before the subsequent steps, 5 to 12 really, will be in 2D. So before we go into the 2D formulas, I want to cover a little bit of ground with some other material, some more finite difference formulas, and some interesting observations at this point. So recall that the 1D diffusion equation, this is the 1D diffusion equation that we used in step, 3, okay? So for step 3, in step 3 of our assignment, we had for this a forward difference in time, right? And we had a central difference in space, right? So this resulted in an algebraic equation for u at time n+1 and each location I, which is the only unknown. In terms of values which are known at the previous time step, which is the time n, right? Recall, that was step 3. We had that, basically we had that the computed values at n+1 depend only on the past history. Okay? So to start a solution, we need an initial condition and 2 boundary conditions to be specified. A formulation of a continuum equation into a finite difference equation which expresses the unknown, expresses one unknown in terms of the known values, is called an explicit method. You can see why. It's explicitly calculated with a simple, unsimple algebraic equation. Each step of the way are only unknown for each point, and we advance in time in a time marching way. Okay, so if you look at, if you consider this, for example, because this scheme right here that we used in step 3, okay, forward in time and central difference in x. I'm going to clear my annotations here to show you a graphical representation of the grid point dependence here. So this is for our forward in time, central difference in x. The formula, you will see that at n+1 has only one unknown that depends on the same mesh value I, the one before and the one after. Of course, we have a central difference, and therefore we have information on both sides of each point I. So I minus 1, I, and I plus 1, and we advance in time for each point I equally. So we repeat this. That's our graphical representation of the grid point dependence. Such a graphical representation that, as I've shown here, is usually called a stencil. And we'll draw a lot more of these. Okay, the stencil kind of shows you the dependence of the different mesh points in one little sketch. Okay, now suppose that the solution has been advanced and that the unknowns at a time, suppose now that unknowns at a time n plus 4 are being computed. So suppose we're at time n plus 4. Okay, then we would have something like this. At time n plus 4, we will have the information from n plus 3 carrying over, similar to the little stencil that I have drawn, but now I'm showing a larger set of points. So one thing that you can observe here from this kind of larger sketch of the situation in the grid is that the information at the boundaries at the same level at n plus 4 does not really feed into the computation at n plus 4. Now, this really is contrary to the physics in a way. For the type of problem that we're solving, this is PDE of parabolic type. In fact, if you from your partial differential equations course, you might remember that this is a parabolic. We'll have a reminder later on in this course about the different types of PDEs, parabolic, elliptic, and hyperbolic. Okay, well, I'll just remind you of that a little later in the course. Maybe I'll do a little pen cast or put some information on Blackboard or something a little later. For now, let's just establish that this is a parabolic equation. For a parabolic equation, the characteristic lines are lines of constant t, and therefore all information at time level, at a given time level, should affect the solution. But we're seeing that our numerical scheme does not receive information from the boundary at that particular time. It only receives information from the boundary at the previous time step. Now, if you're establishing boundary conditions that are constant at all time, maybe that won't affect your solution, but if the boundary conditions are a function of time, then what happens is the scheme lags behind, the boundary conditions lag behind from the scheme in one time step, okay? And this is a feature of an explicit formulation. So in an explicit formula, the boundary conditions lag behind the computation by one step. You see that? Clear? Is that clear? Okay, good. And so we might have a situation in which this is not acceptable. Perhaps the boundary conditions require us to, to be more careful with that. And so one may ask the question, how could we possibly have a scheme that includes the boundary conditions at every time level of the computation, at the proper time level? So that's a question that we ask. So I'm going to clear that and show you, well, I'll just use this for the time being. Or does that disappear? Oh yeah, it does. So, how can we have a scheme that includes the boundary conditions at every time level? For the computations. So for example, consider this. We could, well, remember that we are dancing in time, and we want the boundary conditions, and the central difference formula is the one that is actually going to carry these boundary conditions into our solution. So we want that scheme to be at the same time step as our time derivative scheme. So the way we do this is use a backward difference approximation for the time derivative. And we will have, well, backward difference means that when we estimate the time derivative, we're going to look backwards in time. So we estimate the derivative at n plus 1 point I minus ui n plus, if I do it like this, from the point of view of n plus 1, looking backwards in times, it means that I am estimated everything here at time n plus 1. And I'm looking backwards in time to time n, so I want everything in terms of n plus 1. So this is going to be n plus 1, I minus, plus 1 minus 2 I n plus 1 and plus ui minus 1. This is our central difference in space, right? So everything is calculating at time n plus 1, and the time derivative is looking backwards in time. You see that? Okay. So what happens now is that this equation has three unknowns. Right? We don't know. We got three unknowns. This guy, which is repeated here, and this guy. Three unknowns. And if we look at the grid points that this involves, it would be a dependence of this type. This is our stencil now. To calculate at point I need at the same, and at time n plus 1, I need at the same time level the information at I minus 1 and the information at I plus 1. You see that? So to compute the unknowns here, we're going to require a set of coupled finite difference equations which are going to be found by writing all. So by writing, well, FD formulas for all points. You see that? Everybody clear with that? So this is going to lead to, so if we want to transpose this formula that we have here, it's going to give you, what do I have after that? Okay. If you want to transpose this, let me just clear these annotations, and we're here. I'm going to transfer the expression that you already have written down, and it's going to give us, well, I have a lot of unknowns I'm going to write the unknowns on the left here. So we have nu delta t divided by delta x squared, and u n plus 1. It's all going to be n plus 1 on the left side here of my equation because these are my unknowns. I minus 1, I'm going to write the unknowns on the left, and ui n plus 1 appears 1 time plus 2 delta t over delta x squared times, if you recall, and u at I plus 1 is only multiplied by this coefficient here. And this is equal to minus u n I. And I hope I got those signs right. If not, let me know if you find any sign errors. Okay, so this, you can see here that when I write one equation for one of the points, I'm going to have 3 unknowns with a coefficient. When I write all of the finite difference equations, this is going to lead to a linear system, which if I write in matrix form, it will have a tridiagonal coefficient matrix. You can imagine that from looking at this, which represents just one equation, right? Three coefficients in each row. You can have 3 coefficients in each row, so that leads to a tridiagonal matrix when you write this in matrix form. So you have to solve a linear system at each time step. So that's a little bit more complicated than what we were doing before. This is a formulation which we call an implicit method, a formulation which includes more than one unknown in the finite difference equation is known as an implicit method, okay? And it results in a linear system that needs to be solved at every time step. Fortunately, there are many methods to solve a tridiagonal system quite fast, that algorithms that are canned. Even MATLAB has a nice way to write your sparse matrix. A sparse matrix is something like this, a banded matrix. Of course, you can write them in a very efficient form. Also, in terms of memory, you don't have to write a square matrix of n by n with a bunch of zeros. You just can very efficiently just write the bands of the matrix in your computer to save memory, for example. And there are some fast ways to calculate and solve such a system. So fortunately, it's not too bad. But you can see it's a lot more work than the explicit method. You agree? But there might be certain applications where you would prefer to do this for the reasons I explained earlier. Maybe your boundary conditions, maybe it's not acceptable that the boundary conditions lag behind in your problem, your physical problem, for whatever reason. So this is how the numerical methods start getting a little bit more elaborate to solve such drawbacks. Okay? One very, very well-used and well-known method that is of this category is called the Crank-Nicholson method. A very well-known method for the parabolic type of problems, such as the model 1D heat equation that we were just showing. And this one is obtained very cleverly by taking the average of the explicit and implicit schemes. It's still going to be implicit, but look what you obtain very cleverly. So we take the average of the explicit and implicit schemes. So we consider as a model equation for this discussion the 1D heat equation, the 1D diffusion, and we would have as our transposed form. I'll write the final. You'll see very clearly how the terms come into play. Here you will have 1/2 of We still have this coefficient nu times delta t over delta x always. One of the terms is going to be the implicit term, and so the implicit term for this difference in time will express all of these space derivatives in terms of n plus 1. So you're at the same time level. We have, this is a central difference, so I plus 1, then I, and then I minus 1, so central difference in space, but at the same time level as our unknown. So we have 3 unknowns here, plus 1/2 the explicit version, and I haven't left enough space, but this one is I plus 1 at n minus 2i n I plus u n at I minus 1. You see, we have made an average of the implicit and the explicit formulas for the space derivative, right? Comparing with our time step, with the time level that we're looking at. And what happens when we do this is very interesting, is that we're going to get a second order in time and space. So remember that the previous, for example, in step 3 of our assignment, you don't have to do this in your assignment. This is in the step 3 of your assignment, you just do final difference, forward difference in time, central difference in space. That's all I'm asking you to do at this point. But you can see here that it could get more interesting. The forward difference in time, of course, is first order. And here we just taken the average of the explicit and implicit scheme, both of which are first order in time, and we obtain second order. Yes? Because I have made a mistake in my formula. Thank you very much. Thank you for picking that up. I've made a mistake here when writing these notes. There we are. So, no, of course, it's implicit because we have an implicit contribution here. So it is implicit. We still have to solve a linear system. And we still get a tri-diagonal system to solve at each time step. And you can see that it's second order because remember that we saw before, we noted before that an expression like ui n plus 1 minus ui n over delta t, which is the expression we're using in all of these formulas, can be a central difference approximation for the midpoint, right? Recall that? We saw it for space, but of course it also applies for time. In this case, the midpoint is going to be time n plus 1/2. The time level n plus 1/2. Remember that? So we're using the same idea here, and so we're considering the midpoint. Okay, so let me. I'm going to show you this in detail, but before we do, let me show you what the stencil looks like. Let me see, did I leave space? Oh, I left enough space there. So the stencil here looks like this. For grid point I at time step n plus 1, we have this unknown, but the unknowns at both sides of this, I minus 1 and I plus 1, feed into the formula. We have them here, these guys over here. And we also have the ones from the previous step, right? And this can be considered a midpoint approximation for, this can be considered, let me clear these slides because you already wrote that down and it's kind of messy, so I'll just show you that. And in terms of the grid points, we have a central difference representation of du dt at a point, let me call it A. I'll show you a picture. This is point A. And the average of the diffusion at the same point. So we're looking at the point here in between, and we do that first step, which is the explicit part, and then we do the implicit part to move upwards the other half. So this is delta t halves, and you see this is our midpoint, and I can interpret that as the addition of two steps. So I have a two-step computation where I do first an explicit step going from UI to UIN to UIN plus 1/2, which corresponds to this point A that I drew there. And of course my delta t is delta t halves. And here I look at the diffusion on the previous time step. So this is my central difference diffusion approximation, I minus 1, I, and I plus 1. This is a 1, and this is an n divided by delta x squared. It's an ugly little one. Let's do that. Okay, and then we have an implicit step or sub-step that goes from time n plus 1/2 to time n. So we go now to n. From n plus 1/2, delta t half. And our diffusion term is now, that's the implicit term, so it's on evaluated, sorry, I forgot the plus 1 here. N plus 1, everything in n plus 1. And this makes sense, makes better sense if you look at this stencil drawing. First, we do the explicit step to go to the half time, and then we do the implicit step to get to the next one.